Hello everyone, welcome to Physics 220 here at Grantham University. This is lesson 5 on equilibrium and fluids. So we're going to start with statics. We're going to take a look at static equilibrium and fluids this week. We will see the material and then look at some examples and even some problems. We'll also see a lot of application of the material we learned in lessons 1 through 4. So the first thing we have is static equilibrium. This section is a bit deceptive because there are not a lot of new equations, and in fact there are only two, and that is the sum of all torques equals 0 and the sum of all forces equals 0. What this basically means is that when something is in equilibrium, the sum of all forces and torques are 0 in both cases. Now, this does not mean the object does not have to be moving, because remember the sum of all forces just means there's no acceleration. Just like the sum of all torques being 0 means there's no angular acceleration. So one of the best things we can do is look at an example, and that's what I have lined up on the next slide. So now we move on to an example of static equilibrium. So if you look at figure 9-50 in your text, this shows a pair of forceps used to hold a thin plastic rod firmly. If each finger squeezes with a force, they call them force top and force bottom, equal to 11 newtons, what force do the forceps jaws exert on the plastic rod? So we have to look at this both in terms of forces and torques here. So we see since each half of the forceps is in equilibrium, the net torque on each half of the forceps is 0. So then this is our sum of all torques is equal to 0. So we calculate the torques with respect to an axis perpendicular to the plane of the forceps going through the pivot point, that we imagine the axis coming out of the page. And thus we also set up counterclockwise being positive. So we consider a force diagram for one half of the forceps. So force 1 is the force on the half forceps due to a plastic rod, and the force FP is the force of the half forceps on the pinpoint. Since the FP is on the pinpoint, it does not exert any torque because basically it's at a 0 distance. So then our torque equation becomes the force of the top times the distance of the top times the cosine of the angle minus F1 d1 times the cosine of the angle equals 0. Notice the cosine theta cancels out, and we get a relationship for F1 such that it's F top over d1 dt over d1, or 11 newtons times 8.5 centimeters over 2.70 centimeters. Note we don't even have to change the units to meters because the centimeters are consistent, and we get a value of 34.6 newtons. So our answer here for this example is the force that the forceps exert on the rod is the opposite of F1 and is also 34.6 newtons.
Okay, so let's do another example with rotational mechanics. This was going to use figure 9-47 in the book, so please make sure and reference that before I go through it. So how close to the edge of the 20 kilogram table shown in the figure can a 66 kilogram person sit without tipping it over? First, notice the table is symmetric, so the person can sit near either edge and the same distance will result. If there was a discrepancy in this, you would have to take that into account, and it also would make the problem a little bit harder to solve. Now we assume that the person has a mass big M on the right side of the table, and the table has a mass little m, and it is on the verge of tipping, so that the left leg is on the verge of lifting off the floor. Now another thing I want to bring up here at this point, and this is going to apply throughout the class and even through future classes, is notice many times in a physics problem the case of the variable matters. It can be a little daunting to change variables for the same thing throughout numerous problems, and say in this one we had used m for one mass, and let's say L, for example, for another. So a lot of times in situations where there is only two variables of the same type of thing they will do in physics problems is basically they will use an uppercase and lowercase. In general, we use the larger case to usually correspond to the larger object. So in this one, the person has a mass of 66 kilograms. We use a big M, and the table has a mass of 20, and it has a little m. Alright, so going back on the problem, again, notice the person with the mass of 66 is on the right, and the left leg of the table is about to lift off the floor. If it's just about to lift off the floor, that means there will be no normal force between the left leg of the table and the floor. Remember, the normal force is what the object feels as somewhat like the support force. So there's not going to be any force pushing back. And remember, the word normal here means perpendicular, not so much as our quote-unquote regular definition of normal. So you're going to want to calculate the torques about the right leg of the table so that the normal force between the table and the floor causes no torque. And that's the key here. Again, if it's in equilibrium, there's no torque, there's no rotations involved. Remember, whenever you're solving an equilibrium problem, you always solve it so that you pick a point of rotation as your axis in this case. So counterclockwise torques are taken to be positive. Again, with all rotational problems, you have to set a specific direction for positive and negative. The conditions of the equilibrium for the table are used to find the person's location as such. The sum of all torques is equal to mg times 0.60 meters minus mgx equals 0. Okay, the table is symmetric, so you're treating it as if all of the table's mass is at the center of mass. That's where we get the little m, the g, and the 0.6, minus the big M for the person, g again for the force here, and then our unknown x. So these are both set equal to 0, and that's the key for the condition of rotational equilibrium. So we can set those two equal together. A little bit of algebraic manipulation. Note and be careful, the 0.6 m, that means meters. This little m here means kilograms. And the next step, you'll notice we plug in the values, and we don't have to worry about any issue with units or whatnot. So we get x, 0.6 m times little m over big M, plug in the values. Notice the ratios here of the masses. It doesn't matter if we had measured in kilograms or grams, they're going to cancel out accordingly. So now we get 0.6 m times 20 over 0.66. That ratio is going to be smaller than 1, so we're going to get a value much less, or 0.182 m. Thus the distance from the edge of the table is 0.5 m minus 0.12 m, or 0.32 meters, or 32 centimeters. So this was a good example of how we used some common sense examples. I did examine the use of case in physics also, and we had to do a little bit of the physics beyond this. Like, for example, it doesn't come out and tell us explicitly that the normal force equals 0. We have to think our way through this and think about what it's going to mean before we can apply this, and finally we get a nice succinct answer that helps us solve the problem. So next we're going to move on to fluid dynamics and run through some of the basics there, and then also I'm going to show a few examples for this week, and then kind of wrap it up, and then we can move on to the lab videos.
Now we move on to a brand new concept here in our physics class, and this is fluid dynamics. Fluids are a little bit different, and there's a different way to deal with them. One key point is, since the mass is hard to isolate, instead of working with masses of points, we work with volumes and the densities of the fluids also. Two main properties here are what are called Archimedes and Bernoulli's principles. Archimedes' principle states that the buoyant force on an object is equal to the weight of the fluid displaced, or BF equals volume of the object times the density of the fluid times the acceleration due to gravity. Now this explains how things float. Also it helps us understand when we do some manipulation, and you'll see some examples, that it relates to the densities of objects. An object has to have a lower overall density than the material it's floating in. Now this good example here is like a steel ship. You may think, well, I know, Mr. Hale, steel is actually much denser than water, so it should sink. But if you take the total volume of the ship and divide that into its total mass, you will see that if the boat actually floats, then the density is lower, because there's a lot of open air in the compartment in the space that contributes to the overall density, not just the density of what the material is made of. Now the next thing we have is what's called Bernoulli's principle. And this is a little complicated, and it relates fluid flows and pressures at different points in the system. So what you're assuming is there's 2 points in the fluid flow system you're looking at, a 1 and a 2. And we have that P1 plus 1/2 rho V1 squared plus rho GY1 equals, and looks very similar to the other side, P2 plus 1/2 rho V2 squared plus rho GY2. Now the one thing I've been talking about here is fluids, and I haven't made the distinction between a liquid and a gas. And they actually behave very similarly, except for one stark difference, and that is a gas is usually compressible. Meaning if you were doing an equation with Bernoulli's principle, for example, if it was a liquid, you would more than likely assume on both sides of the equations that the density, or that rho, is constant, whereas a gas, you could not make that assumption. So I have an example to end this week, and otherwise we're moving right along. So now let's look at our first example. This is a 0.48 kilogram piece of wood floats in water, but is found to sink in alcohol, in which it has a parent mass of 0.047 kilograms. That means that's how much the buoyant force is canceling out the weight. So what is the specific gravity of the wood? Now, first I want to point out, all specific gravity means is when you express the density of a material in terms of the density of water. Okay, so if it had a specific gravity of 0.5, that would mean its density was half that of water. So the difference in the actual mass and the apparent mass is the mass of the alcohol displaced by the wood. The mass of the alcohol displaced by the wood is the volume of the wood times the density of the alcohol. Okay, so it's literally giving us the amount of matter that the wood is displacing. The volume of the wood is the mass of the wood divided by the density of the wood. And last but not least, the density of the alcohol is its specific gravity times the density of water. So putting that into equations, we see that M actual minus M apparent equals rho air times V wood, which then is rho air times M actual over rho wood, which is then going to be equal to the specific gravity of air times the rho H2O times the M actual over rho wood. So we can manipulate this equation and see that rho wood over rho H2O equals the specific gravity of the wood. Plugging in what we have from above, we get then our relationship for the final answer, the specific gravity of the wood, which is specific gravity of the air times M actual over M actual minus M apparent, or 0.79 times 0.48 kilograms divided by 0.48 minus 0.047 equals 0.88. Okay, we have one more example for this week, and it also brings in one more new aspect, and this is called Torricelli's theorem. So basically, this deals specifically with velocities of fluids leaving the bottom of a container at a specific height. So the question asks, how fast does water flow from a hole at the bottom of a very wide 4.6 meter deep storage tank filled with water? We're going to ignore viscosity here. So we apply Torricelli's theorem, which is equation 10.6, that says V1 is the square root 2g times the height difference. So all we do is we take our difference in height, which was 4.6 meters, plug it into the 2 times g, and we get the answer is 9.5 meters per second. Well, that wraps it up for this week. Please take a look at the 2 other lectures also. If you have any questions at any time, please email your professor.